Greetings in the love and light of the infinite creator. I'm Andrii Zvorygin, joined here with Simon Michaux, Dune, Jed, Ivor, Dan, Roger, and John. And Simon will be doing a presentation on the Prometheus Nexus project and nuclear, and then we may have follow-ups from Dune and Dan about geothermal. All right, Simon.
Hi guys. So hello everyone. So I'm going to give a briefing tonight of where things are at with Promethean Nexus and Vulcan Catalyst. What's been happening is I've been spending most of my efforts getting Thorium molten salt up and running. So I'm going to give a briefing on that first. Okay, so how do I share? Hang on, where is it? Start screen sharing. Got it.
Yeah.
Got it.
Mm-hmm.
Entire screen.
Mm-hmm.
Rock, rhythm, and roll. So, all right.
Yep.
And, okay, can you see that?
The purple transition. A solution set. Okay.
So this is actually a fragment of a previous presentation I've done. So this was to describe the purple transition. The full presentation is 2 hours. I'm not going to give you all that, but this is just to say what we're doing. So what is thorium molten salt? Compared between uranium and thorium. Energy return on energy invested calculation for the thorium MSR. That's going to raise a few pulses. The status of MSR development and some industrial projects that could be developed, which I hope to actually, all of which I hope to deploy in Promethean Nexus. Okay. So, and if we get to it, there's a new form of transport I'm proposing. All right, conventional thinking. Every time I talk to people, I don't know if people have noticed this, but at the moment, when you actually go out and talk to anyone at the moment, for the last 12 months in particular, it's like someone shitting their brain. It's like all critical thinking is stopped. They've disengaged, they're keeping their head down, they will not talk about anything unconventional. And so we ended up with this. So this is the 5 stages of human grief with a few steps added in.
Mm-hmm.
You'll recognize all this. Shock and disbelief, it starts. No, that's not real. Followed by denial. Once you get past denial, you get anger and aggression.
Mm-hmm.
Then there's bargaining. Then there's guilt. Fear and anxiety was something Chris Martenson proposed.
Okay.
Then you get depression, and finally we get acceptance. And so we tend to either get one of two ways of going. And when you sort of go through, well, what do we do? So what about peak oil? So we'll use gas. What about peak gas? We'll use coal. What about coal? We'll use nuclear. You know, and you can't pin them down. And the other one is the green transition's the way. And so it's either one or the other. Mm-hmm. And there's a general reluctance to see anything else outside of that. Right, so at the heart of all this, and this is not something that's actually part of many discussions, but I insert it, our industrial system has to simplify in complexity and shrink in size. So it's a fundamental metamorphosis of everything. And yes, so the future will be smaller and it will be simpler, whether you like it or not. And I make the case that thorium is a useful fuel. So the 2 primary fuels going forward are thorium and, get this, human sewerage. So the fate of the current system is this. We all see it. It's not the end of industrialization, it's the end of the way of it happening the way it is. And a new system will be developed where necessity is the mother of invention. But what is that? What form will it take? And the real question is, how do we resource this? So what are we trying to do? We want electricity, transport, and manufacture. We want reliable and consistently stable power generation in all weathers and all geographical regions. Concentrated form with a low materials footprint, a long working life, like 12 years. That's bollocks. We need to do better than that. Mm-hmm. And when the systems come offline, they have to be designed to be recycled with a minimal waste plume and a very low environmental input. Okay, so get past this. So what I am trying to get the people around me to look at is we're in real trouble here. And if human innovation is to have a snowball's chance in hell, we've got to be have a realistic understanding of what our limitations are, but then work with what we've got with an open mind and open heart. And if we don't do that, our duck is cooked. So what do? Well, victory loves preparation. We need a plan. So
For sure.
So the resource balanced economy is the heart of everything. We've got to change how we manage our resources. And in fact, while we're chatting, I was chatting to my mate Charlie Hall, and something he said has inspired me to do the following. I'm going to take the resource balanced economy that I developed. This was Jacques Fresco's resource based economy, but with energy terms and a few other things added to it. I'm going to develop it using the ecological system, biophysical systems thinking found in ecology. So I've gotten hold of Howard Odom's textbooks on how to actually do systems from an ecological point of view, and now I'm applying it to industry. And I'm using Charlie Hall's biophysical economics to do it. This will be a substantial piece of work. When I'm ready to hit one out of the park, the target I'm trying to get is this. Well, we've got the Wealth of Nations by Adam Smith. We've got Das Kapital by Karl Marx. I propose to write a third alternative of a similar caliber.
Wow.
If I can hold it together, that's the target, and it'll probably appear in a couple of years. We're talking about another nasty 1,000-page monster. Sorry about that, but that's what's going to be. Okay, so liquid fuel fission systems, thorium molten salt, electric vehicles by different battery chemistries, combustion of iron powder to replace coal in manufacture, but we recycle that iron powder with the pyrolysis of human sewage, and ammonia fuel ICE for some applications in maritime shipping. Spine rail transportation network, and the use of photosynthetic materials, mainly from forestry. One of the case studies I'm about to show is a group from Norway is reinventing the forestry industry using thorium systems. And what they're proposing is amazing. For those who are interested and have got the minerals for it, pun intended, go to this report, and it starts on page 477 of the PDF. This is the GTK report I wrote for the Hawaii report. Right, so thorium. To maintain existing capacity, we need thorium-fueled nuclear energy. And the reason I say that is I've been through a few systems now. I have not found anything that's going to help us out of the mess that we're in, apart from this. There is another system, but it's theoretical at the moment. And what I'm talking about there is the zero-point energy and the electrogravitics system that comes from that. But so that'll be a supplement to, we need industrial heat. And we need an industrial scale energy. And I like the thorium molten salt solution for now. Prepared to be shown something better, but that's what I like for now. All right, just quickly, what is this? So we take thorium, and we make it into a thorium fluoride salt. We put that into our reactor, inside the shielding. We use a proton lamp. We don't even need a plug of uranium anyway. A proton lamp to irradiate part of that salt with protons and neutrons, and that transmutes some of the thorium into uranium-233 through a couple of steps. Once it becomes uranium-233, it's generating its own neutron economy. That uranium-233 is hot, it melts the salt into a liquid, and that liquid passes around the system. Huzzah! It worked. All right. So heat exchanger, that heat then turns water into steam, and the steam turns to generator. The generator generates electricity. There's two things preventing this from melting down, or three really. One, it's already liquid, and it's not under pressure, so it actually can't melt down. If it gets too hot, what's called Doppler broadening will actually make the neutron economy cascade over the top of itself, and it will shut down. So there's an atomic limitation there. Also, there's a freeze plug. If it gets too hot, this melts, and all the fuel goes into dump tanks, which means it can be taken away and dealt with separately. All right. So that's the report from 1972 for the technology. It works. That's the system. The Chinese are already doing it. Yeah. So I went through and published this mass balance. This is actually a conventional uranium solid fuel generation 3+ system. for 1 year's activity. So I actually worked out, what goes in for uranium fuel and what have you, and what comes out in terms of waste. So 36.9 ton goes in and 31.6 tons come out. And that's all our radioactive stuff. So that's the first. So what I'm trying to do is compare the systems directly. I then got the Fuji system that was published in 2008. It was running for something like 30 years in Japan in a research context. I scaled up to match the capability of the Generation 3 Plus reactor, what goes in and what comes out. Okay, so we're consuming most of the fuel, only 3%. All the fuel gets consumed, and of the fuel going in, about 3% it goes into isotopes that are still radioactive, and they need to be stored for 300 years, not for longer. All right, to generate. You've seen this. I'll step past this. Okay, so this is the idea if we were going to compare the two. So this is the amount of spent nuclear fuel produced. It's got to be on a log scale so you can tell the difference. It's an orders of magnitude smaller at the front end and at the back end of the fuel cycle. Okay, why solid? So solid uranium pellets go into these rods, and so we have what's called a fuel rod assembly. And that's most of it is uranium-233. Uranium-235 is the isotope we need, but 96% of the mass is uranium-238, and that's after enrichment. Then we've got the problem of the stuff on the surface tends to shield the stuff in the center. And so this is when the fuel rods become, more trouble than they're worth in terms of, the neutron economy. That's when they absorb neutrons. They've got to be taken out. Most of it's still radioactive. Liquid systems, everything moves against everything else. And uranium-233 is the isotope we need. All fuel comes in contact with all other particles. There is no shielding, which is why we're consuming all of the fuel that goes in. The waste product is very small. So the waste that comes out of uranium systems, solid uranium systems, is mostly uranium-238, which is very radioactive and hot. And then you've got isotopes, uranium, plutonium, what have you. Right, so if I take uranium-238 and I bombard it with neutrons, and I'm not too worried about it just takes longer than normal, it eventually becomes uranium-233. That's the fuel we need to run the MSR. So the MSR system, the molten salt reactors, can run down the spent nuclear fuel stockpile and turn it into energy. So the Achilles heel of nuclear power can now actually be consumed. So
that's great.
That's one of two problems that the environmental movement has with nuclear. Okay, hang on to your hats.
Hey, Simon, before you get there, quick question for you. Did you compare that to harvesting plutonium and then further enrichment speaking specifically of whether or not you're looking at a MOX process for recycling of the spent fuel into usable fuel for, I guess a traditional uranium or plutonium based Gen 4 reactor?
Simple answer, no. Because I just didn't have the bandwidth to do it. Yes, that's a useful thing to look at. Once you actually open the gate, there is literally hundreds of engineering and scientific engineering paths to develop. And yes, that's one of them. I did do a MOX simulation in the 2001 report where I was just looking at solid fuel, but not in liquid fuel, no. And that's an obvious path.
Got it.
If someone could get off their ass and actually give me some proper funding, I could do a proper job. Saying that part out loud. All right. So we all know about energy return and energy invested. Now, there's a lot of so there's this is the Fizan and Court 2017. They did like an estimate for over the decades. Oil peaked somewhere around 1950, and it's been on a downward slope since then. Gas peaked somewhere around 1940 or 1935, something like that, and since then it's been declining. This is rough. Coal is still increasing, and that's coming down to the economies of scale technology associated with mining. But put it all together, fossil fuels are on their way out. Now, this is a blunt tool, and there's a lot of papers in the literature now that have corrupted the tool, where there's a disagreement about how we should calculate this. But you look at the numbers, anywhere for, say, oil and gas is 10 to 45. You can conventional nuclear, one source has it at 15-1. Another source I was looking at the other day has it at 60-1. But all our renewables are under 10-1, which is under the threshold that is actually useful. Right, watch this. This is thorium molten salt reactors. So these numbers here, the conflict is what do you put in the calculation and how far do you go? Like wind and solar, if you include batteries, these numbers go negative. Now, this is thorium. Now, for every gram of thorium or uranium, we can actually, it generates 24 megawatt hours of thermal heat for every gram. Now, to make the fuel, thorium oxide can be just made into a salt at any mine site. It's a very simple process. There's other things to add, things like beryllium and lithium-7, which are a bit more boutique, but it's not as complicated as all that. Over 60 years, which is the working life of one of these systems I'm about to show you, that's the thermal heat and that's the electricity at the efficiency ratio. So build the plant, start the neutron reaction up. This is the energy cost. Heat the fuel to get it going, produce the fuel over 60 years, purify and clean that fuel over 60 years, offline maintenance, transmission to the user over 60 years, harsh language, the beer index, the Christmas party, decommissioning the system at the end of life, transporting spent nuclear fuel waste over 60 years, process that waste over 60 years, and a partial share of the construction of long-term waste storage for the SNF generated over 60 years. Now that calculation set has a greater footprint, a greater cost set than any other energy return on energy invested calculation I've come across. Now, so you divide these two numbers together, hang on to your hats. The energy return on energy invested for thorium molten salt reactors is 2,548 to 1. For those who are interested, go to this report and that page in the PDF. So let's so 2,500. So to put the 2,500 up against these numbers here, it is orders of magnitude better.
Yeah, for sure.
So,
and we got Charles Hall.
G'day, Charlie. G'day, Charlie. Love your work, mate. I was just telling everyone that you've inspired me to take on a new, major new piece of work. All right. So, how long will the resources last? If we took electricity consumption for 2022, for globally, that was 29,165 terawatt hours. So if we did that each year, and that we would generate that with both systems in a thought experiment, these are all the reserves and resources for uranium, all the way out to speculative and unconventional resources for uranium. That would last 29 years if we were to generate electricity at that rate. Thorium that we know of, assuming we can actually access this stuff, which is, once you say the word resource, the answer is no, you can't. That's 1,300 years. But if we were to actually put uranium and thorium together and the spent nuclear fuel stockpile, now the number comes up to 6,000 years. Right, so,
Well, that will give us enough time for geothermal transition.
No, that's enough time for humans to fuck up the biosphere more than we can possibly imagine.
I think we're actually in the process of being forced into learning a few things before this is actually possible to transfer. So while this all looks very good, it doesn't actually solve any of our problems. I think we're going to be forced into seeing a few things and learning a few things the hard way, in a don't touch the stove, it's hot kind of way. And then we get to the good stuff. All right. So I went out to the Copenhagen Atomics factory. This is me with the guys. This is a 40 megawatt system of electricity or 100 megawatts of thermal heat. It's modular, and they fit in a shipping container. All right, that's the actual schematic. That's the system. It's an onion configuration. They've gone to extreme lengths to make sure that no radiation at all comes out of these things. They're walk-away safe. The only thing that they are not able to deal with is if someone hits them with explosive and blows them up. Everything else, it's safe metric. That's the size. So it's the full system. I actually went out and saw these things. It's a little taller than a conventional shipping container, but it's the same length. It arrives on a truck. What does it cost? They've now got capex purchase of 50 million euros, which is about 58 million US dollars. OPEX, and this is actually coming out, maintaining it, and doing it's about 2 million a year, and that translates to projected cost of electricity 1 cent a kilowatt hour. So that is the OPEX there. So, and the current commitment is Copenhagen Atomics will change the unit every 5 to 25 years, depending on the fuel condition, how it's going, for free for 30 years, and they'll do all the radiation handling and waste handling and all that. This is the proposal, where we've got like a modular system. So where each one of these shipping container sized units, that's each one of these, and you swap them out like a cartridge, and they are modular, so you can stitch them together. At the moment, I think it's started, but it's a secret. I hope it's a secret. In Switzerland, there is a test taking place. It starts this year and ends next year. It's a 12-month trial. Then factory production starts in 2028, and deliveries are running from 2030. They're promising a production capacity of 10 of these units a year. When I was at the factory, they said they were going to produce 1 a day. And from what I saw, that's not a problem, because these things are about the complexity of a 3-bedroom kit home. The real problem is legislation and permitting. More on that later, because what I have to promote to show you today is actually some movement on that. All right, Samsung in South Korea has now got the design of not one but several large ships now. So this is a natural gas carrier. They're putting an MSR power system in it. So if it works as promised and it's actually out and running, this is a ship that will never have to refuel for a long time, years. It could just keep going back and forth, and it wouldn't have to refuel.
Mm-hmm.
So, yeah. And so...
it's kind of like, we have nuclear aircraft carriers and nuclear submarines. This one is similar concept, just with thorium. Right.
So what was I saying? So our geopolitical adversaries are doing this now. China's doing it. It is believed Russia and India are having MSR systems as well. It's the BRICS economies. We're being left behind. But this means it's about to break out into the Western world. There's another thorium system. This is a pebble bed. This is actually safer again because it's not liquid. There's nothing to leak. The problem with the MSR system in principle is you could have a leaking pipe, and you could have like leaking radioactive fuel on the floor. It can't go aerosol, so if that does happen, someone's just got to come and clean it up. And presumably you'd have it in a room with shielding. Right, but this is a pebble bed system. So the idea is you've got this cylinder, you've got these pebbles, and you put the pebbles on the top and you pull them out the bottom. Now, conventional solid fuel thorium has an issue of if you put like thorium pellets in, the outside of the surface oxidizes and they become useless. So while it's radioactive, you've got to take it out of the reactor, acid bath it to clean the surface, and then put it back in the reactor. And that's considered a pain in the ass and not worth a hassle. Just use uranium. This system, you take a kernel of about 0.5 millimeters. The best combination is if you have thorium doped with uranium. And around that you have like a couple of layers of compounds with graphite being the final layer. So it gets to about 60 millimeters. It doesn't oxidize. What that means is the entire kernel can now be used for radiation. So you pull the pebble out the bottom, test it. Is it still producing heat, as in it's still radioactive? If it is, put it back in. And if it's not, send it off for reprocessing. The reason I like this system, so this is a system that was installed in China. It runs with uranium pebbles at the moment, but the same technology will use thorium, not a problem, like without a change. You could put thorium system in at the moment. The the capex is higher because you're lots of concrete buildings around and everything. But what I like about this is it produces heat up to 950 degrees Celsius. And once you pass 900 degrees, all sorts of industrial processes are possible. Now, conventional nuclear can get you about 300. Thorium molten salt gets you to 560. To get up to 900, if you get to 900, you can use the sulfur iodine cycle to produce hydrogen. But all sorts of other industrial things become useful. There's no meltdown risk. There's nothing to melt down. So this is inherently safer than the MSR system, which is inherently safer than the uranium system, and so on and so forth. Okay, so the next thing is this has come from the Norwegian people. Conventional thing is can put hydrogen. How do we make hydrogen? So these guys are innovating technology where they use a combination of thermal heat and electricity together. So instead of your conventional hydrogen fuel cell, it's both together. If you've got thorium thermal heat, which is costing a projected 0.5 cent a kilowatt hour, half a cent, then we'll be able to produce hydrogen at 10 cents a euro a kilogram. And that changes the equations for hydrogen, as in the hydrogen economy. So this is what the Norwegian guys are actually looking at in terms of market price. So heat, half a cent a kilowatt hour. Electricity is 1 cent a kilowatt hour. Now, to put this in context, electricity, say in South America, for Matrix for industry is about 13 cents a kilowatt hour. And in Australia, I think it was 6 cents a kilowatt hour. So this is much cheaper than what we're doing at the moment. Okay, so industrial projects. This is the sort of thing. So for every tire here, if we had a thorium reactor, what we do? So I'm going to produce diesel fuel by recycling rubber tires. So this is the sort of thing I actually want to put in Promethean Nexus. All these rubber tires, like Hawaii is producing 750,000 a year. And so this is Australia. There's just stockpiles on them. They just don't know what to do with them. So each tire, depending on its size, contains between 25 and 85 litres of oil at the point of manufacture. So it's less than a worn-out tire, but there's quite a bit. And every now and then some twat sets fire to them, and that becomes a real environmental problem to these stockpiles. The other thing I'd like to work with is end-of-life tires at mine sites. So you've got big mining trucks, and tires wear out. They're huge. Every mine site's got a stockpile of these tires they don't know what to do with, so they just bury them. And so each mine truck wears out something like 6 tires a year, which is a full set. They've got so the Escondida mine in South America has started with a fleet of 40 haul trucks, and now it's got 188 over 36 years. So if you take 6 tires per truck per year, then 1,128 of these tires were produced in 2024 alone. And over 36 years, 21,500 of these tires were produced and then stockpiled. Okay, I want them all. What do I do? Go to the mine site. It's got trucks. And with trucks come tires that they don't want. I want to get paid to be taken or take them away. Thank you very much. Okay. So the problem with these tires at the moment is handling them. Like, what do you do? And they tried putting them in shipping containers and transporting them to site, but they're so big. So the idea is to cut them up and debead them and shred them at the site in a mobile plant. And all these things fit in a shipping container. Put the shredded stuff in a shipping container, put it in a truck, which is taken to a pyrolysis plant, which just happens to be the Promethean Nexus Vulcan catalyst project. And it just happens to have an MSR unit, thank you very much. And we're going to run the pyrolysis plant. The pyrolysis is heating without oxygen. The rubber breaks down into a liquid, and that liquid can be put through fractional distillation, and you've got solid char, which is carbon black, syngas, which is useful, steel scrap, and an oil. And that oil can be distilled, some of it, into saleable diesel fuel. We then use the diesel fuel to run the trucks that transport the stuff. And here's a bonus. The solid char that comes out, carbon black, can be used to make carbon fiber and graphene products. So, cheap electricity, cheap diesel fuel, and cheap high-tech products. Money.
Nice.
So, and we can produce diesel at an approximate 1.2 cents a litre. And that's your pyrolysis plant there. So, okay, so the prize is this. Put it into a pyrolysis plant, run it with thorium, you get pelletized rubber and rubber products like gaskets. Carbon black comes out, steel scrap and fuel oil. Take the fuel oil, it becomes, through distillation, a diesel fuel substitute. Carbon black goes through spheroidization, you get graphene production, and then put that through 3D printing applications and what have you. So here's your mobile plant to cut the tires up in the first place. And so here's the metrics. For those who are interested, go to this report, which happens to be the Hawaii report, page 1299 on the PDF, and you're away. Diesel is produced at 1.2 cents a litre.
That's very cheap.
That is, and so now, okay, now we're going to try the same trick, but at sea. Out at sea, there's lots of plastics. That we've been dumping plastics in the ocean for decades. We've got all these environmental issues. And I'm hearing a lot of shit. I'm hearing a lot of people talk a lot of shit about this sort of stuff. It says we need to get in there and do it with an industrial action. Lecturing each other in conferences isn't going to do it. Right. So for every square mile of ocean, there's about 46,000 pieces of plastic, and they're all sort of being pushed together in what's called ocean gyres. They've been increasing tenfold each decade since 1945. We're talking about a lot. Again, for those who are interested, go to the Hawaii report, page 1319. I can give you the link for this, and Andy, if you like.
Sure.
All right. So here is the map of the plastic gyres. This is like, they're everywhere. So Hawaii, this is the Hawaii report, is right next to the biggest one of them all. That's like the size of Texas. Send ships here. Right. So what are we talking about? So for every hang on. So for every 10 foot, for every foot of coastline, we're getting like 10 bags full of plastic. So an island of trash twice the size of Texas is in the middle of the Pacific Ocean, right, which floats to about 30 feet below the surface, and that is this thing here. Size of Texas, and in the center of it is like 10 meters deep, or 30 feet. Right, so we're talking about 1.6 million square kilometers. The currents are pushing it all together, which actually helps, because now we can harvest it all at a relatively small place. Most of it's really fine. Like 92% of the mass is larger than 0.5 centimeters, but the real problem is the stuff of microplastics, which are like, like 1 or 2 microns in size. That's what's really harming the natural life. Okay, here's my plan. Take an oil tanker. It's engineered to carry oil already, long trips for the ocean, large deck space, and soon they're going to be really cheap. Put a pyrolysis plant in it. So plastic waste goes in. Now this has struggled in the past because usually when you get all the plastic out of the ocean, the ship fills up and you've got a ship full of plastic. You've got to take the ship out to back to shore, transport the plastic from the port to the recycling plant, and the economics and it's really difficult. The other problem is keeping enough volume up in a consistent form. Right, so if you're out in the ocean and the largest patch of plastic in the world, that's not a problem. So the idea is to take the actual process plant out to the area. So rip out the oil tanks, not all of them. Put in a pyrolysis plant. Run it with a thorium molten salt, which also runs the actual whole ship. Put a scoop on the front to collect the plastic. Broadcast a sonar frequency to convince any wildlife to get out of the way.
Okay.
So what do I mean by that? Right, so engineer a device that will broadcast so it's uncomfortable. Anything that's actually able to leave will. Right? Mm-hmm. So the plastic waste is collected, and the larger pieces, larger than 3 millimeters, are taken up a conveyor belt into a sorting station. That conveyor is monitored closely by people and cameras run by AI. When an animal is observed trapped, personnel will step in. At least one of those people will be a veterinarian. The animal's freed, the animal's looked after, and it's returned to the sea. Okay, so collect the scoop, collect the stuff, put it into a sorting station, wildlife rescue, reject objects are dealt with, put it through a shredder, put that through a gravity jig. The water that's less than 3 millimeters, put it into a centrifuge, and then put that through gravity spirals. Water's returned to the sea. So what we're doing, and the microplastics, which are the real problem, also put it through a centrifuge. So what we're doing is we're sorting plastics into classes by mass, by density, and that'll make it easy for the pyrolysis. We've also got fibers, which is all the toilet paper, and metals. Okay, so that's our stuff going in. Put it through a wash plant to actually clean all the salt off. We've got a thorium system on board. Right. We take seawater. We put it through electricity generation after desalinating it through a multi-stage flash system. Make potable water. That's our wash plant. The brine water is returned to the sea. So salt water is brought in, salt water is taken back. Put it through another centrifuge, and then we've got a pyrolysis plant run in batches of density. So you've got liquid biofuel and your distillation column, and we're making diesel. Right, so we're taking plastics out of the sea and we're making diesel again. Right. And we've got other byproducts. So here are the numbers. For those who are interested, go to the Hawaii report. This page 1319 in the PDF. So what we are doing is we've got 4 10-ton systems for 24 hours running in parallel. So we're taking 40 tons of plastic out of the ocean a day. We're producing diesel fuel at 2.8 cents a litre. So, so that's the plan for that. So these are the sorts of things that you could do. Produce fresh water while generating electricity. So take seawater, put it through what's called a multi-stage flash desalination unit that is run by the thorium system. Salt brine comes out. We then extract all the salts, and we make steam that runs the turbine. So then we get electricity. On the other side of that turbine, that steam has had most of the energy taken out of it, but it's actually desalinated completely. You've got to desalinate the stuff to put it into the turbine so you don't corrode the turbine. So that's actually fresh water. So the idea is to pump it uphill into a reservoir. This is the idea where the sites I like are anywhere on the west coast of the South American continent, where you've got it's desert that no one wants, and there's water problems there. There's water shortages and electricity shortages. Catch in a reservoir, put a mineral balance in it so it's useful for life systems. Gravity feed it back down the hill. That's our water source. And then the electricity goes off to whatever we're doing. And here's our multi-stage flash unit. So the idea is we take seawater in and you put it through a heat exchanger, and it goes through. So heated seawater is passed through a series of chambers where the pressure is progressively lowered. And as it lowers, the decrease in pressure causes a portion of the water to flash and vaporize. That's collected into fresh water, and on we go. And we keep doing it for the efficiency window of the system. So, take our seawater. We're going to generate steam with our thorium system. We've got brine on the other side. Put that through a solar still. A solar still is, for example, like a container, like a concrete bath with a glass ceiling. The sunshine comes through the glass. The water evaporates and condenses on the glass, and then drains off into a series of drains. We're producing sea salt, which can be used directly as it is, or we can strip the metals out of it. So this is the thing where there's metals of all kinds in seawater. Okay, so salt extraction, which can be used in the chemical industry or battery production. You can make batteries out of chlorine, sodium, magnesium, lithium, or potassium. So, but also a lot of chemical operations start with salt. And so then then we get electricity, heat transfer, and that's our fresh water coming out. Okay, so here is how I would use that. So in Australia, we've got this endearing little process called fracking. Now, you've got it in the US as well. So for every, say in the Permian Basin, for every barrel of oil that is produced, 3 barrels of polluted water is produced at the surface that are full of chemicals, which is a real pain in the ass for the flora and fauna. So the idea is this: put it through a multi-stage flash unit run by a thorium system.
Dan had a question.
Oh, I've had up my hand for a while.
Yeah. It was just
I can't see any of this. So you need to tell me, Andy.
oh,
Yeah,
okay.
well,
Sorry.
I've had it up there, but anyway. So your molten salt reactor, your issue there, I think you've already kind of pointed is the metal alloy, whatever you're going to use. So all the metal alloys that I know of that you could use on that corrosive molten salt contains nickel. They're what's called delayed neutrons. Delayed neutrons, there's an isotope of nickel that outgasses helium particles, so it turns into foam. And then you got fluorine involved in it, but get neutronic damage, and that's where you leak out. So, and the other thing is you have to do 5 years worth of testing, has to do with this isotope thing before you allow this out in the public. And then remember, you're dealing with fluorine gas, which is really nasty stuff. So but when you're talking about this frac water, it's an issue with it. It's not 3, it's 5 barrels for every barrel of oil we produce, and the water is radioactive. It's got uranium and thorium, mainly uranium. Uranium dissolves in water, so that's the biggest issues with the frac.
Right. So the corrosion issues with the MSR have been resolved.
I'd love to know what the metal alloy that they use.
So it's a commercial secret.
Okay.
Now, but my mate Harold Sverdrup has been through the Copenhagen atomics system, the engineering, and he has told me personally they've resolved the problems. The Chinese have also resolved the problem. So whatever they've done, it's
well.
manageable.
But the thing about the Chinese, supposedly this reactor's been running for the last 3 years, and we've got nothing that's come out of China. So we don't know what happened there.
I've been China is dodgy. This is the problem. But I presented in Hong Kong, and I spoke to a governor of a province who told me that the system in Gobi Desert's been running commercially since 2022 to sell power. The World Nuclear Association, Nuclear News Association, have confirmed that they've got the license. Whether that's true or not, I don't know. The Chinese guy told me that they are actually in the process of producing several hundred units now.
So, okay. Well, then there's another thing you've got to think about. And this goes, and understand I'm talking about this because most of my family is nuclear Navy. Okay. So I have family members that go back to the birth of this. So on an aircraft carrier and a submarine, those are small reactor cores, but we use water for shielding from the neutrons and absorbs 90% of the neutrons. And the thing about having a smaller core is they leak neutrons and turn everything around it very radioactive. Since your reactor doesn't use water for shielding, that means everything around it's going to become very radioactive from using this type of reactor. The other thing is that oxidation problem you're talking about, that was an issue back in the 50s. We solved that by switching over to using zirconium instead of using stainless steel or aluminum. So
what they use, this is the onion configuration. What they've got is a blanket of thorium fuel. And so the neutrons that are coming off the system here is being used to create more fuel. We've also got heavy water that's being used. That's how they deal with that. These things are a commercial secret, so they won't tell me exactly.
Well, even just looking from the outside that you've got it, I can tell you don't have enough shielding from the neutrons coming out of that reactor.
So
unless you're using solid thorium metal itself, it's just not dense enough.
What can I tell you? They've passed the safety specifications of Switzerland to run this.
Okay. Well, all I can say is we're going to have to sit back and watch.
Right. So there's a trial happening right now. Well, it's either right now or soon in Switzerland for the next 12 months where they've passed all those metrics.
Okay.
That trial will be published. Then you've got the system that's going into the ship. So is it real is what you're really asking. Have I actually seen one of these systems? No, I haven't. But I've been told.
I'm not being down on the whole thing. I'm giving an example, Simon. One of the things we have to deal with here we have a number of companies that want to build small modular reactors here in the United States, right? But the only small modular reactor that's actually certified for civilian use in the United States is actually the Westinghouse reactor. And the reason why is because the United States Navy, we have 70 years worth of safety data on that reactor. Everybody else has to go through this process where they go out to the Idaho National Engineering Lab, rent out space, build the reactor out there. right? Test it for 10 years before they certify this design, before you can actually start deploying, reactors out in the, out in the 50 states in the United States, and they have to go through that whole certification process. So this whole thing
that's happening now. That's happening now. So Copenhagen's been running for 10 years of testing, and before they actually formed Copenhagen, they was running for a couple of years before that.
Yeah, and it's got to go. We've got to have a fissioning reactor, though. That's the thing we've got to see here.
So that's what's going in Switzerland now. So
I know TerraPower and all those companies have been doing simulation so for years and years and years, but until we actually, like I said, at the Idaho National Engineering Lab is an R&D center for nuclear power, and that's where you actually, put reactors on the ground and actually go into the actual process and production.
So I'll say again, the people I'm doing business with, and I've actually spoken to the Switzerland people who are actually running the test. They've actually told me that this thing's actually passed the safety things, and they're actually doing a full radioactive test.
Yeah.
So this thing, whatever it is, it's a commercial secret how they've done it. I've also spoken to the group in Australia that's actually done the corrosion testing. The corrosion testing, and that's been going on for a couple of years now. Right? So whatever they've done here, there are multiple organizations saying it's real.
Mm-hmm.
If it's not real, I've got to go back to the drawing board.
Fair enough.
No, I'm just saying, I'm trying to understand how we have this really shortened testing cycle in Europe versus here in the United States. We have this 10-year testing cycle.
Okay.
It's been going for 10 years.
Yeah. That's the question. I don't know what the answer is.
Can we continue the presentation for now? And
sure, go ahead.
We can get back to it.
The issue is we created a bureaucratic landmine that has basically shut down nuclear for the past 40 fucking years.
Right. So all I can tell you is the check.
Well, I disagree with that. One of the things growing out the INL, most of my family's nuclear, all the nuclear accidents they've had out there. So that's beside. I'm sorry. Go ahead.
Okay. Right. It's real. Do I have to come back in 12 months with a picture of me standing in front of it before you believe it? Fuck me.
All right. Let's get back to the presentation.
Okay. So where I'm actually proposing...
I had the same problem with geothermal, Simon. I'm sorry.
I can spell geothermal as well. Yeah. Okay. So the idea is that a lot of fracking water was come out, and what I would like to do is clean up this water, but then actually use the cleaned water in agriculture. And that will solve two problems at once, especially in Australia. They grow a lot of cotton in an area where that's drought restricted, and it's Chinese farmers that are doing it who don't give a shit about the local communities. And so if we can take wastewater and turn it into potable water for agriculture, that's how I'd use it. Okay, pyrolysis of human sewage. So what you do, take human sewage, put it into a system run by a thorium system, and produce syngas, which is a mix of hydrogen and carbon monoxide. You also get biochar and bioliquid, which is useful to produce organic fertilizers. Okay, all right, so that's enough of that. So let me go to the next one, case studies. So, oh man, I'm having... What's your problem here, huh? Okay, can you activate? Right. Right, okay, so there's a series of case studies. In a presentation I put together recently, there was how will we use thorium? And so in Finland, there is an industrial cluster around 2 towns, 40,000 people. There's a steelworks, smelter, mine sites, and a port. The next one was a mine site. How do we actually completely decarbonize a mine site, including the haul truck fleet? And if you use thorium at 1 cent a kilowatt hour, you get a 26% decrease in OPEX. I can't show you that at the moment because I'm actually trying to get that published in a paper. Port of Rotterdam, what they looked at? The nation state of Germany. Right, so if Germany did this, the purple transition, it's a plan where they'd never have to speak to the Russians or the Americans ever again. The Nordic frontier, this is a system that might be of most interest of you, is an integrated network of MSR systems across Finland, Sweden, and Norway with a completely reinvented forestry industry. And then we get to Promethean, Nexus, and Vulcan Catalyst. All right, so get through all this. We've seen that. Yeah, whatever. Yeah, come on. Yeah. All right, so case study 1. So Kemi and Tornio in Finland. So here's Finland, and here is the cluster. Okay, so you've got the town of Kemi, which is there, and the town of Tornio, which is there. So 2 towns, about 40,000 people. You've got a harbour that's industrial. You've got an integrated steel complex, and you've got a natural gas liquid terminal, and you've got a chromium mine, and it's all integrated together into one system. You've got a fibre mill and a similar operation owned by the same company. Okay, so these are the needs. So 40,000 people, you're just below the Arctic Circle. So we've got an annual heating bill of 209 gigawatt hours. And annual electricity is 135 gigawatts. This is the electricity demand for the industrial group. This is an industrial cluster. This is the total thermal energy consumption, which 67%, 6 or 68% is thermal fuels, things like gas and coal. Okay, so the approximate cost of electricity in this area is around 21 cents a kilowatt hour. And that's something like 28 million euros for electricity. So if we took one of these systems, 40 megawatts of electricity, and it runs at 1 cent a kilowatt hour as promised, so you end up with one such unit could generate all this for 1.35 million euros of electricity and 1 million of thermal heat, with an additional 255 gigawatts of thermal heat left over. So one thorium system would do both towns. This is for the civilian population for their electricity and their heating up near the Arctic.
Mm-hmm.
So industrial systems. So we need to produce. OPEX costs of around 42 million and euros, or 49 million US dollars. So the thermal energy breakdown. So this is the thermal energy. So something like 46 million OPEX for euro. Put it all together. Okay, so domestic needs, electricity, industrial needs for electricity, thermal needs, and the number of units we're talking about for this whole region is 26. So 26 shipping containers and associated turbo units that come with it. We're talking about an estimated capex of 1.3 billion. Case study. Next case study. This is the port of Rotterdam. So it's a big port. Most of the stuff going into Europe goes through this port. 13.8 million TEU. This is like shipping containers, where 1 TEU is a 20-foot shipping container.
Oh, okay.
Their power generation capacity is 10 terawatt hours of electricity, and 11.7 terawatt hours of thermal heat are needed. And this is what the seagoing vessels need. It's the equivalent of 250,000 households. So it's the equivalent of like a small city. And it's a big site. This is 105 kilometers squared. And so 17 kilometers is the total length of the internal roadway network. Right, so here's your map. At the moment, they've got 3 power plants. So first one's a mix of coal and biomass. Then the next one is natural gas, and the last one is coal and biomass. And that's what they run at the moment. 21.7 terawatt hours a year is what they're demanding out of this system. So the proposal was this: replace the fossil fuel energy generation system, and then produce some hydrogen as well. And then actually, because you're producing a lot of heat and hydrogen, move a series of industrial systems into place. And instead of actually, at the moment when they actually pull out forestry mass, they use about 60% of it to make things like building materials. The rest of it they burn in combined heat and power plants. If they hydrogenate that instead, it would turn into a biofuel. So could they then use that? This is the thinking. So these are the guys who do the Nordic frontier case study, which I will talk about shortly. So you've got a thorium system. It's generating heat, electricity, and we're making hydrogen in the same complex. We're pulling in stuff from outside. We've got a lot of residual biomass, and so these are your saleable products coming out. So this is actually being modeled as a system, and this is what's being proposed. So stage 1 is planning, stage 2 is 2 units, 3 is 8 units, and 4 is 40 units. To do the whole thing together, we need 60. You need 65 of these systems together. So this is the overview of the unit. Yeah, go on. Yes, was someone?
No, I just said but there was a question in the chat of what is the minimum community size for an MSR unit? Because I thought it was like 55,000, but then you showed that example of 2 communities, each was 20,000, and there's multiple MSRs.
You could have one thorium system sitting between those 2 towns, and it would service both towns.
Okay.
Right.
I see.
So, yeah.
I was wondering about the heating because they look quite a bit of ways apart.
So that is something that he'd have to do it in the Arctic. There's a lot of energy required for industrial applications in both of those towns.
Mm-hmm.
So the reality is we're talking about... Oh, let me go back to that case study. Where is it? Okay, here we go. So... Okay, so we need 26 units between the 2 towns.
Okay.
And so what you do is you'd have a number in each cluster, and they'll be spread everywhere.
So you'd have multiple of these MSR units.
Yeah.
Okay.
Okay. And they're modular too. You can put as many together as you want to get the generation that you need. Now, this is a very simplistic study. The actual engineering of actually applying this, is going to be different and more complicated. So this is not even scoping study level thing. This is just conceptual.
Okay.
So Rotterdam. Okay. So we need 65 units. There's a planned 50. So here's the overview of the systems. You've got the thorium unit. You've got a heat exchanger. You've got a 3-stage turbo system, and you've got your electricity generation there. Here's my pointer back. Yeah, and so this is and so you've got a Rankine engine heat regenerator that lifts the energy efficiency by 5%. So you've got a total of 55%. And Copenhagen Atomics is in the stages of talking about commercial exchanges for this. There's a lot of maneuvering in the background about who gets the first systems when they sort of come out, and so there's a lot of money being thrown around. Here's the market price of what they're talking about. So again, 1 cent a kilowatt hour and half a cent for heat. And so they think they can, for example, make electricity for 1 cent a kilowatt hour, when in the Netherlands it can be up to 50 cents a kilowatt hour, depending on the circumstance. They can make hydrogen for 36 cents when the market price is 8 to 12 euros, and so on. So. All right, so to the first stage, we're 2 thorium units and a turbine group to come with it. We're talking about 180 million all told. And you got your OPEX. And so when the whole plant's written off, it's about 6 million a year. Proper maintenance is probably 50 years, 60 years is what's been projected. This is what they're promising, though, to make sure they come in on target. So if hydrogen was offered significant amounts below €1 a kilogram, then industries will look to move to the port of Rotterdam. And so if that works, then we're out the gates and running. Okay, so now this is the spine rail idea that I've had, a new form of transport. So this was around the port of Rotterdam, you've got several distribution centers. And this is the idea of moving goods. And the idea was, you have the underslung system that would have your shipping containers move back and forth, and you'd have monorails on the top. So this is based on an idea I saw in Nigeria, where they're moving stuff from a mine site over an 80-kilometer track to move ore, and the same system can move shipping containers. And the idea is this. So here's Rotterdam. and make one 250-kilometer track, which actually will then move most of the shipping containers along that route. So it's a 250-kilometer cargo track. So in this Hawaii report, page 487, electricity consumption of the freight cargo, if you were to move a shipping container on a fuel cell electric vehicle truck, so it's a truck run by hydrogen, you're going to consume about 4.5 kilowatt hours a kilometer. The underslung cargo pod system will move the electricity consumption is, by the time you make the hydrogen and use the hydrogen, so the underslung system at 1.6. There was a question there. And Andrew,
Did Dan has a question?
I just wanted to ask Simon, what's the advantages of this over to say like the current rail system we have right now? What are the advantages of this?
Okay, there's the capex of setting the system up because it's when you actually put in a rail system, it tends to be quite expensive. Whereas this system here, it's the same basic principle. It's like a light rail, but it's, instead of actually sort of having like a civil engineering berm that's actually got to be perfectly level, you've got a series of metal stilts and you suspend it, which means it can go over all terrain. You don't need to prepare it. So the capex for the system's much, much less. And so the idea was you have a monorail over the top to move people, and your people are on one system and your freight's on another. It's essentially the same idea as rail in a different configuration. The difference will be in the capex to set it up. So the idea is to have it lighter so you can actually sort of move to more parts of the city. So the Futran idea, over 82 kilometers, they estimate $1.25 billion US, with a capex of around $3 billion a year. So for 82 kilometer system is 1.25 billion. For a 250 kilometer track, we're now talking 3.25 billion. And so if we go through the numbers that calculated, you end up with this. So remember, it's going to cost 3 billion to do this, 3.25 billion. So these are the systems. This is the shipping containers that need to go to each one. So 1.3 billion TEUs. If we were to run it with, say, a fuel cell EV truck, so we're talking 1.28 terawatt hours. If you were to put it through the cargo pod system, just the cargo pod system, we're talking 456 gigawatts. Now, if you were to have a conventional cost of electricity, you've got that ratio, 265 goes to 94. But if you were to put a thorium system in there with 1 cent a kilowatt hour, it drops to 4.6. So 265 drops to 4.6. And that's two technologies put together. Germany? Oh, so yeah, was that a question?
Well, yes. I was thinking about this, but like I just have that like bit of a feeling of counting your chickens before they hatch, kind of thing. Because while we do have this as kind of the theoretical how much the electricity will cost, I think that we will see when it is implemented.
Well, here's the problem I've got, Andy, and this is starting to really give me the shit, actually, because to actually get proposals to put a thorium system on the ground, people say, oh, it's not real. Then they say, oh, why do we bother? Why can't we go with the conventional systems? And then you've got to say, well, this is why we do it. So you've got to show these kinds of analyses.
Right.
And they say, oh, why don't we use solar panels? Why don't you freeze to death in the dark?
Fair enough. I agree with you that it's worth trying out, and I believe you that they have the safety testing and working models and things like that. It's fine.
Put it this way. If I don't have anything else on the books that would work beyond the conventional prepper, go back to the 1880s level of prepping. There's no other technology that comes even close to sorting out our problems. If we don't do this, then go back to the idea of horse and cart. Yeah, and so and that was the old plan. So this looks like it's working. So it's just a case of, well, it's about to drop, and if it does drop, I want to be part of the solution, not be left behind.
Fair enough. Yeah, no, this I think this is really good, like, because thorium, I mean, sorry, not thorium, geothermal would just take way too long. So if thorium, I mean, it has its place, and we have, you know, I guess we'll talk about that more. We already have a big geothermal build out, but it's just the thorium molten salt reactors, if they get going soon and they're proven, that will be very good and give us more time to do a transition to geothermal or anything else in the future.
To have anything close to resilience, you actually the ideal is to have like multiple energy generation systems.
Exactly.
And they all do different things.
Yeah.
And so I'm actually a supporter of the geothermal revolution as well. All right. So Germany, and this is an intellectual thought experiment. But if what would you? So this is what Germany. 2019 is the last year of sensible data. After that, we had the COVID pandemic, supply disruptions, and there's weird artifacts in the data. So this is what they consumed. They also produced a small amount of coal and gas, and they have those reserves, which are pretty small in the scheme of things. Electricity generation, so they use these sources: oil, gas, coal, nuclear. This is back in 2019. I bet they're regretting shutting down the nuclear now. So, but 609 terawatt hours for the year. And that's how it's split up: industry, residential, what have you. They had that amount of solar and that amount of wind in terms of installations at the time. So the German transport fleet, so they had 64.7 million vehicles. And this is the fuel they consumed. And so diesel was the primary fuel consumed in Germany. And that's going to be a real problem if the ideas of we're marching into a diesel shortage actually come to fruition. Right, so the idea was to turn some of this into an electric vehicle transport fleet and some of it into a hydrogen fuel cell fleet. So if we did that, okay, so we've got 1.47 terawatt hours to charge 55 million electric vehicles. So then we've got hydrogen fuel cells. There's a whole lot less of them. These are the heavy vehicles. 565,000 and 150 terawatt hours to make the hydrogen. And so we're talking 2.9 million tons of hydrogen annually. So then I mapped the German industrial system in terms of what each thing was, how much heat they needed, and what have you. And so and the amount of energy required. So I went through the whole thing. This table took a while to put together. So this is the amount of thermal heat that they needed. And so, all right. So given that, right, the temperatures less than 600 degrees you could probably do with a thorium molten salt reactor, because they do 560. Anything from 600 to 1,000, they needed the pebble bed gas reactor. And so this was the actual thing that we need there. And so anything more than 1,000, this is where I go to combustion of iron powder. So it's a metal fuel. It's the same metal fuel, iron powder they use in the powder coating industry, so we know how to do it. Each ton of iron powder contains regularly now 1.9 megawatt hours. And they know how to do that now.
I just have a question. Is this more economical than electric arc furnaces?
Yes.
Okay.
Electric arc furnaces have their place, but they can't be used for everything in all applications. You really do need a thermal fuel.
Okay. What industry do they use it in?
So this is the well. Let's go back to this.
If you're reducing iron oxide, you've got to use a fuel to remove the oxygen.
Yeah,
like hydrogen, carbon for coke. Yeah, that's the idea.
Okay, so these are the industries where we need the heat, right? Mm-hmm. And so the idea is you use a number of systems together and you use the iron fuel, but the iron fuel is not destroyed. When you burn pure iron fuel, it becomes iron oxide, rust. And so you can recycle it. Mm-hmm. And so so we need, this is the amount of heat, terawatt hours that we need, combustion of pure iron powder. We had an annual availability of 81.8 million tons. And at 0.6 megawatt hour a ton to actually produce it, we need 49 terawatts to produce the stuff in the first place. However, if we put human sewage into a pyrolysis plant, we get Syngas. Right. So pure iron powder gets turned into iron oxide. So 81.8 million tons becomes 117. We need to put that into a syngas atmosphere at heat, run by a thermal system, and we can actually strip the oxygen back out and recycle that iron powder into sponge iron. So the mass syngas we need to do with that, and that will come from 3.9 million people of annual sewage. So what that means is once you've got the iron powder, you can recycle it. Now, the guys that are doing this in Netherlands have recycled it, fuel cycle it 5 times now, and that you lose something like 0.5% in mass in each recycling that goes through the flume, and they're looking at ways of reducing that. Because,
the iron oxide powder.
Yeah. So you take the iron oxide powder, you burn it, it turns to pure iron powder, you burn it, becomes iron oxide, put it into a syngas atmosphere, and the oxygen gets stripped out, and you get iron powder again. And so sponge iron, and so that cycle you're losing about 0.5%. So sewage for 3.9 million people. Germany has 80 million people, so that's doable. So that's how they can actually run their systems. Heating. So at the moment, this is what they do for heating at the moment, and it's mostly coming from natural gas. Natural gas, like 9.5 million houses, and also heating oil. So the idea, this is what they're pushing in Europe at the moment: fifth generation heat pumps. These things cost money. Who's going to buy all this stuff? Well, that's a conversation. But if you use fifth generation heat pumps, you need 59 terawatt hours of electricity to do it, if that works. I'm assuming it does. I would do things a little differently if I was to do the engineering myself, given with what I understand. Anyway, so they've got 966 terawatt hours of electricity. Now we originally started with 609, but now we've got all this extra stuff we've got to do. To do that, we're talking about 3,291 MSR units and 138 pebble bed units.
And is this for the entire industrial production of Germany?
It is for the nation state of Germany, both domestic and industrial.
Oh, okay. I see.
So hydrogen, we would use 61 tons of thorium in 139 tons of fuel salt, and we would recycle 81.8 million tons of pure iron powder, and we'd need the sewage from 3.9 million people to do it.
Okay.
How much thorium we're talking about? So we're talking about 139 tons of fuel salt, 61 tons of thorium to do it for the year. I haven't included the heat for 950 degrees because I haven't. I've got the information. I just haven't got around to doing it. But if the German state did it, they would gain control of the whole energy value chain. Where they'll be able to do things internally inside their own domestic borders.
Do we have that much thorium on the market right now?
So thorium is not wanted on the market. It's seen as a waste product. The nuclear industry has got stockpiles of the stuff that they're storing. They don't know what else to do with it. In America, they have monazite sand that they're burying again just to get rid of it.
I see. Okay.
We have millions of.
So thorium is 3 to 4 times more abundant than uranium, and all of that thorium is useful, whereas only 0.7% of the uranium reserves that we've got actually is uranium-235.
Oh, okay.
And every nation state has thorium in some form. What would it cost? Right, so given that capex is 50 million euro, so on, a 1 gigawatt plant is 1.4 billion. So to have the whole fleet built in Germany, and remember this is a thought experiment, we're talking 164 billion euro. Put this in context, renewable energy plant investments over the previous 4 years has been 58.9 billion, and 76 billion has been sent to the fun and games in Ukraine. And so
there's a question from YouTube. What's the full round trip system figure EROI for the ag food sewage combustion proposition?
That I don't know. I haven't actually sort of done it yet. What I do have is it's a closed system. I take a waste product and then I run it Yes, the thorium systems are required. I think it's for every ton, it's 264 megawatt hours. Yeah, I've got the numbers, but I haven't actually done the full system sort of calculation. That's a time thing to get around.
So, from what you were saying, if the thorium ends up being over 2,000 EROI, I think it'll be fine.
That's a woolly number, and
Yeah.
there's engineering that's got to go into that, and it's a new technology, and we've got to learn how to use it. There'll be things that we don't know, right? So it's not going to solve all our problems. It's giving us a path.
There's a follow-up question from another YouTuber. What about Jevons paradox? If it's as cheap as efficient as Simon suggests, wouldn't countries implementing it just explode in industry and consumption?
So humans are dumb. They do dumb shit in an organized fashion every now and then. Humans suck. This is why aliens won't talk to us. Jevons paradox is a real thing. So yeah, that is a risk. Before we actually get to the point where these systems are widespreadly available, I think some of our other problems that are on the books are going to manifest in a way where pain is a great teacher, and we are going to have to learn a few things the hard way. We also have to completely re-engineer everything because it's a fundamentally different technology. So we've got a number of hard decades ahead of us. If we get through that, then we can. Then you've got the Jevons paradox. So, whoa, we're rich now. We can do what we want, and it starts up again. I'm of the opinion that we are on the cusp of understanding that our environmental challenges are actually ecological in nature, and planetary boundary geochemical in nature. And once we actually understand that, some of our dumbass decisions might actually be changed to something else. So on one hand, we've got a lot of challenges in front of us, perhaps the worst in history. On the other hand, I do feel it is actually possible for at least some of humanity to get with the program and stop being so foolish.
Yeah.
That's all right. This is the one I was hoping to show you. So Nordic Frontier. So this is interesting. I was invited to attend a private conference in Norway, and I found myself in a room full of billionaires who own a lot of the industrial systems across Norway and their CEOs. We're talking about 20 people.
Nice.
And one of them was a general from the Norwegian Armed Forces, which was very interesting to talk to. And they were looking at developing this project. What they're talking about is developing a network of molten salt reactors across Norway, Sweden, and Finland. So this is Harald Sverdrup's work again. So this is the basic idea. We take minerals and we take biomass. The priority here is to revolutionize the forestry industry, and we're going to make high-tech building materials out of biomass. Once we've actually got high-quality energy and thermal energy and electricity out in the forest at the stump, and that changes things. And so we're going to go, and so there's a series of systems that have been put in place to model this. So this is the thinking where you've got, all right, so you've got your thorium cluster, and then you've got your bioclusters around that, but you've also got your metallurgical clusters. The idea is to also turn every deposit that we know of in the region into a mine, produce that mine, but sell the concentrates only to operations within those countries for things like smelting of metal. So you're looking at an internally self-sufficient circular economy evolution, and so on. So this is the energy unit. So the thorium system, there's your heat, electricity, we're going to make hydrogen, and with the biomass coming in, we're going to hydrogenate some of that biomass into a series of oils which are useful in various forms. So here's the plan, or the plan at the moment. Every little square you see is a thorium reactor, molten salt reactor. The black lines are existing rail, and the red lines are the rail systems they want to make. And so the idea is to have a decentralized system. So you've got electricity at the industrial site itself, hydrogen in industrial amounts, where you use it as you go. You don't have to store it. a network of fully developed mines to smelter operations based on known mineral deposits, heat generation, and hydrocarbons from biomass. And so the fuel that will come from that can be put into internal combustion engines, which will allow some of the existing systems to stay. And support for an integrated Nordic defense system and strategy. Now, I've been personally invited to help make this happen. And so
Nice. Congrats. I see that most of the reactors are pretty far from the border with Russia. Hello? I can't hear anyone. Okay. Try again. Hello? Simon, are you saying anything?
Can you hear me?
Yeah, I can hear someone.
happened there?
Ivor.
What happened there?
Okay,
Something
there.
happened to Simon's. Okay.
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 Now you're back, Simon. Okay, yeah, I didn't hear.
Okay. 1, 2, 3. Was it beer is good, wine is better, whiskey is best?
Okay. I could
right.
hear. Yeah, my question or my notice was that there's only seems to be 2 of the MSRs in Finland.
At the moment.
Okay.
The Finnish were invited to the party, but they the forestry industry in Finland saw this as competition, so they said no.
Oh, I see. So how's the forestry involved here exactly?
Okay, so in Norway, the Norwegians have got the money, right?
Okay.
And if you're not employed by the forestry industry, you're employed by the government, and that government is dependent on oil revenue.
Okay.
Right. Now that's only going to last 30 years. Even if they decide to phase it out, it'll take 30 years to phase out. So the forestry industry is the primary industry in Norway that what they're sort of happy about. They recognise that this originally came about because they did the math where wind turbines were supposed to be used to generate hydrogen to allow all this to happen, and they worked out that the number of turbines they needed, it was never going to happen. The LKAB mine site, which I believe is that one there, it's a mine site for iron ore. That's actually where they've got the hybrid system where they're going to make hydrogen steel in a hydrogen atmosphere, and they need a vast amount of hydrogen to do that.
Mm-hmm.
So they've done the math and they've realized that only SMR technology in some form is actually able to actually help them here once oil and gas are knocked out.
Mm-hmm.
And so they've done the math. This group is actually talking with Copenhagen Atomics to be their customer. They want to be their first customer. What's happening is the trial that's in Switzerland later this year. That's in progress, or it's either been it's about to start as in progress, and when it finishes, they are planning to purchase that system and put it in Luleå, which is there.
Mm-hmm.
And so they want to put it in Luleå, or they want the first demonstration plan in LKAB, which is the iron ore site. They are also talking to Swedish Parliament with regard to what the thorium MSR systems actually are and how they could be used, and they're getting legislation changed over the next 24 months. The Norwegian Parliament is also watching what's happening, but they want the Swedes to do it first. And this is because they're dependent on oil revenue. They don't want to be first.
Okay.
The Swedish have a problem where their ability to be energy self-sufficient was knocked on the head with the intervention of the gas industry through lobbying, and they are very enamored by everything Brussels tells them.
Mm-hmm.
And so everyone's playing pass the parcel in the good old in the days of the pass the parcel, the fastest game in the world in the Irish post office from years ago. Yeah. Anyway, so they're all waiting until the music stops.
Mm-hmm.
So the forestry industry is the goal for both Finland and Sweden. This group also happen to own all the industrial metal smelters. Harold Sverdrup his family happens to own a mint, a bullion mint, which says he's a good bloke to know.
Mm-hmm.
Anyway, so he's they're actually getting the law changed while these trials are sort of going on. There's another game plan to actually sort of get this sort of developed legally as well. So legal action's happening at the same time as the economic stuff is actually in progress, and they're in regular contact with Copenhagen Atomics. And I've recently been introduced to this group. I've asked them permission to actually present this, and they agreed. So, okay. So there's also a group in Australia that again did all the corrosion testing for Copenhagen Atomics. I'm talking with them too, and I'm trying to get the two groups to talk together, and that will be the Thorium Molten Salt Supergroup. Finland was originally invited to take part in this. The forestry industry is going to reinvent itself. It's going to completely metamorphose, where everything gets re-engineered, where you've got high-quality heat and electricity out in the forest right next to each operation that's actually there. And so you have industrial clusters where everything sort of coordinates together in a synergistic form. What I call industrial permaculture is now being planned in this system. Now, yeah.
So you mean like short rotation willow coppices, like for fuel wood, or are they doing lumber and you're using the electricity for
all of the above?
Okay.
No. So all of the above. They want to make, instead of burning biomass, which is what they do a lot of the time, they want to make high-tech biomass building composite materials.
Okay.
That's where the money is. And instead of burning stuff, they want to hydrogenate the waste product into bio oils.
Okay.
And so then the chemical industry starts up around that. So we're talking about a fundamentally next generation forestry industry with the idea of high quality heat and electricity in a decentralized network that's actually optimized together as one system. But the forestry industry will lead. The metals industry is secondary. Finland was invited, but the forestry industry in Finland, which is also like the mining industry in Australia, saw it as a threat, so they killed the idea. So Finland was decided to say no. Well, that's unfortunate because the next generation system was being designed and formed, and their own customers could be part of that. So now we're trying to get Finland back at the table, but now through the minerals angle. But there's a whole lot of industrial stuff along this coast here, which would benefit from this greatly. So this is when they revolutionized the forestry industry to produce high-tech construction materials. So this is their plan. So this is the system that's actually been put together, and what they're slowly kept. These are the people with the money. These are the people who actually want to actually build this stuff out. So it's not like a university group that talks about publishing papers. Right. Although I suspect that's what they want me to do for them. And so the idea of industrial cluster, where you've got multiple things coming together that actually would feed off each other. And they would take stuff from all over the place and actually sort of in a synergistic point of view, bring things together. So this is the green steel in Boden in Sweden, where they're going to make hydrogen, and they're going to make the hydrogen in steel in a hydrogen atmosphere. So they're going to have green steel sales, but they think they're going to have excess hydrogen and excess heat. That'll be remarkable if they do, because the quantities they're talking about are pretty amazing. So the old coal-based European steel is being outcompeted because the European political mismanagement of the energy production and market regulation. The new political paradigm towards energy is required to avoid European global industrial redundancy. That ship has sailed, unfortunately. The Swedish hybrid system technology is a world-leading method which will make the Swedish steelmaking most competitive and completely carbon-neutral system in the world. So, what are they talking about? The thorium energy is the new joker. It's faced 50 years of repression, and so there's a lot of people who say, "No, it's not real," until it is. So the biomaterial revolution and geomaterials are now coming out. Geomaterials, geopolymers, take rocks and minerals and 3D print them. Change coal to hydrogen in metallurgical processes and in most places where coal is used. Hydrogenate the biomass, making gas and bio-oleum and biomaterials, and process intensification. So this is chemical industry, new unit operations. Everything happens also on a smaller scale. Because the power systems are small, you can now have pilot scale units sitting around them, but you have multiple different operations feeding off each other.
Yeah, I have a YouTube question here that's related. It says, did he bring up about biochar yet? Carbon back in the soil, fertilize the land long term. I was thinking about how that seems to be kind of where this is going, in terms of instead of burning the wood, it would be turned into, well, carbon sequestration products.
So the idea is to actually produce a series of products which could be used to go into organic fertilizer. But vast amount, part of the Promethean Nexus plan, and this is a part of these guys as well, as it turns out, vast tracts of land worldwide have been sterilized through industrial agriculture mismanagement. And the idea is to balance that mineral systems and bring back the soil food web. But you've got to use industrial capacity, industrial quantities of organic fertilizers and organic biomass to do it. And so the idea is to have a merging of industrial systems with biosystems to do precisely that.
Like permaculture, to like
permaculture, but at before we get to the permaculture, we're going to regenerate and rehabilitate land that's been destroyed.
Right. Yeah. You got to rebuild the soil that's washed away.
And so the idea is to rehabilitate whole tracts of land and then leave it go fallow for a decade or so, then come back. Because at the moment it's just completely sterilized. What we're talking about here is the co-location of industries, logistics, and modular and energy and generation. So it's a revival of the old industrial combine, where you've got like multiple industries together that feed each other. So there are engineering solutions, and then we can get to Promethean Nexus next. Some of them are unorthodox, get out of our own way, yada, yada, yada. Okay, so the end point here is what helps us, the phrase that helps us for me, biophysical, holistic systems thinking with open hearts and minds is the key to our evolution.
Amen.
But now I've put that together for my thinking after spending a bit of time talking to Charlie. So Charlie, if you're listening, thanks, mate. You're influencing what I'm doing.
Well, good. It's kind of blowing my mind.
And so,
there's just a few more follow-up questions from the YouTube. They were asking, job of replacing oil and gas. How about feedstocks for fertilizer, plastic, and asphalt? Is that part of this plan?
Say that part again.
Feedstocks for fertilizer, plastic, and asphalt. You already said about the fertilizer, and I guess bioplastics. I guess the asphalt would be the one that maybe not addressed.
So asphalt is something that needs to be attended to. Yes, it's part of the plan. I don't quite know how to mass balance it yet because I haven't got there yet. But it's like I'm trying to actually do the entire thing. Oh man, I've got a few bugs in my system. Asphalt is
we'll have lots of asphalt when the United States takes over Venezuela.
Right, yeah.
This is why aliens don't talk to us.
Yeah.
My theory for what's happening in the BRICS economies, it's coming true, and it's you can see it in the oil and gas industry data, and so this is my model, and if maybe we'll get around to talking about it later or some other time, but anyway, so what would it look like if we designed how we did things based on what we know now? And so that's the Promethean Nexus and Vulcan Catalyst idea. So we need two things to happen. We need an innovation hub that has a mandate to look at unorthodox ideas. There's no shortage of ideas. There's lots of ideas all around us, but for ideological reasons, we reject them. But some of those ideas need to be demonstrated, as in, don't tell me, show me, at a pilot scale so investment can actually happen. And so now we need talking about, well, it needs money and capital. So what are we talking about? We need electricity in reliable quantities, we need heat. And that has to come from somewhere. All of these systems have to have a natural source. Somewhere, somehow. Then we get our raw material resources. Where do we get them from and what do we do with them? And a lot of that comes back to the technology we're using to do all this. So this is the Promethean Nexus project. To paraphrase Jacques Fresco, I never met Jacques. I would have liked to have, though. If we were to design a human settlement, let's call it a city, and we use the best science to had to offer, but we optimize the whole city to the well-being and quality of life for the people who live there, what would it look like?
This is Le Corbusier's idea, I think.
So
Le Corbusier, the architect, I think it was, who had a central city based on the old cities and rail lines going out with agriculture and so forth like this. It's not a new idea.
Fresco came up with this idea in the 1940s, I believe. And he's been talking with people a lot, and I'm actually taking from Fresco's ideas. So no, it's not a new idea.
Yeah.
So the vision is this. Here's the innovative part, Charlie. Someone actually goes and does it. All right, so we're going to evolution of the existing industrial society powered by an unorthodox but mature energy source, operating to a new resources management paradigm, also known as the resource balanced economy, with a more responsible relationship with the planetary environment, a new paradigm in social contract and how we might live. We will construct a technology innovation hub in an unconventional city to the purpose of developing a new energy, raw materials, and manufacture paradigm operated by a more socially mature kind of society. So we're going to have a decentralized energy system. So the idea is...
that's the rub of socially mature. In the United States, which we're going backwards.
So
Russia's going backwards.
Here's my cunning plan, Charlie. Instead of solving the problems for 8 billion people, I'm going to round up a small group of like-minded people, disappear over the horizon, set up shop somewhere, come back in 10 years and do business with whoever's left. And by demonstration, we'll either be more successful or we won't, but we'll actually have a go at being better. But do it on a small scale. Well, everyone else learns the hard way.
Yeah.
Whether that works or not, let's see. Instead of giving into despair, I'm trying to do something. So,
yeah, no, it's a good.
A new relationship with the natural environment, reimagined, restructured transportation network, a change in what money is used for. And that's another conversation again. A development of a new social contract. So new technology has a way of radically transforming what is possible. And so what we call game B, so evolve that into form. The resource stewardship. So the resource balanced economy evolved from the resource based economy. Thank you, Jacques. Circular economy, where we talk in circles. It's actually partial resource sourcing, but the steady state economy for long range systems, boundary conditions. All of that gets integrated together into a fundamentally new system. The goal is to simplify the complexity of the existing industrial network into a smaller, self-sustaining system. Run society on a smaller number of components that are in the simplified systems and manufactured from resources sourced locally. Right, so we develop a more comprehensive plan for so-called reclamation with human beings, technology, and nature will be able to coexist in a long-term sustainable state of dynamic equilibrium. And this is my wife, after hearing me mutter, she actually had a crack at visualizing it. And this is what she drew.
Nice.
I've made a website. So this is the website for Promethean Nexus. It's a strategic project to develop the long-term plan. And it goes through the basic ideas. Okay, so when I actually start talking about this, especially to money people, they said, if I was to give you my money, how do I get it back? And why should I pay for a new social society? And I go, here we go. So they needed a vector to get through it. So that's what Vulcan Catalyst is for. So Promethean Nexus is the plan. It's the long-range plan. How do we get there? Vulcan Catalyst is an industrial project that will raise revenue through the sale of cheap electricity, diesel fuel, and graphene products. So it will also pay for the foundation for, and once it's actually sort of the investors are paid back with that money that we generate, we build Promethean Nexus. So what we're trying to, production of electricity, thorium molten salt reactors, desalination of drinking water from the sea while generating that electricity. Half of which, the steam produced, we only need about half the steam produced for the industrial applications, but also for the settlement drinking water. The rest can be used to green that part of the desert and run agricultural belts. Production of syngas from the pyrolysis of human sewage. We can either make cooking gas or recycle iron powder and run a small smelter. Production of diesel fuel from recycled rubber tires. The idea is to set up shop near a mine site. Hang on, we'll get to that later. And production of exotic materials, all of which will cost a fortune on the market. Okay, path of development. We will produce and sell cheap non-fossil fuel electricity and cheap diesel fuel. Approach a locally positioned company like a mine site that needs large quantities of energy and has no idea how to stay in business once fossil fuels gets knocked out. Collaborate with that corporation. Let's say it's a mining company. Let's call them Anglo. Get them to request the local government to create what's called a regulation sandbox. Within that sandbox, we've got permission to do research and develop it out in the desert far away from people. We want to run and operate Generation 4 SMRs. And we also want to construct and trial innovative building materials. Establish Reactor Park, which is 3 to 5 SMRs, thorium and uranium of different manufacturers. Sell some, but not all, of the electricity back to the mine site. Some, but not all. Use some of the electricity and heat to produce saleable products. Now, a mine site has got lots of truck tires. It's a real problem for them. Get paid to take those truck tires away. Cut them up, turn them into fuel. Sell some of that diesel fuel back to that mine site. And then fund the Chrysopoeia Institute. So here's the Vulcan Catalyst website I put together. So the idea is you say, okay, we're going to make some money. We're going to make some industrial systems put together. Now, what this will do is it will secure the land. It will have a workers' village, which is the starting seed for the city. It will put in place all the industrial units like the thorium molten salt systems, the distillation towers for the pyrolysis plants, and the multi-stage flash units, and the piping of seawater from the coast into the system, and the irrigation up to the reservoir. So it's going to pay for all the industrial assets. With the money and revenue that we make from that, well, that's what we use to develop the rest of the plan. As part of in the Vulcan Catalyst is to use the idea of industrial permaculture, a constellation of industrial pilot scale plants. Each plant is about the size of, say, a domestic 3-bedroom house. And so the idea is to start off with 1 or 2 of these operations, but over time, bring on board more systems as they come in. And it's all integrated together where the outputs of one are put into the inputs of another, and it's all optimized together. And all of this is on the train line, the spine rail train line that goes in and out of the city and across the system itself. And that's Vulcan Catalyst. So the development stages of this. Is someone mumbling in the background? Was that a question?
Oh, no, I think that's some feedback from Charlie here. Hold on. Okay, go ahead.
I'd like to ask a question.
Oh, okay. Go ahead.
For a given level of production, and that means everything, 1 production unit, 1 unit of GDP, if you wish.
Yeah.
What's the footprint? What's the footprint that would be required compared to the footprint today? That's question 1. And question 2, what's bothering me, speaking as an ecologist, about all of this is it's sort of a engineer's view of things. And I think you could sell it to the world better as an ecologist's view of the things, in which you take Ed Wilson's idea of you need to have at least half the world in natural systems to balance out everything else. And can you do it by your method to reduce the footprint of all necessary technology? In other words, it's all the same stuff you're talking about, but going backwards from we're going to try to institute Ed Wilson's idea of greening the earth with natural systems.
Mm-hmm. So let me show you another slide, which is a different way of going about things.
So my first question is, per unit of industrial production, is your footprint going to be larger or smaller with this system? So, I think you can argue smaller because you don't have to mine all the coal or whatever.
Correct. But it's going to be smaller in size. It's going to be much simpler because we make less things. Mm-hmm. But all the things we make, we've got to do ourselves locally.
Yeah.
So on one hand, it's smaller. On another hand, it might be more complex.
Well, I think if you start your arguments that way, it's got a greener perspective. That's
okay. Try this for a game of soldiers. Yes, I have to evolve, Charlie. So I'm going to listen to what you say and have a crack at evolving. Right. So this is somewhere on the west coast of South America. It's desert. There's 6 millimeters of rainwater a year. It's a bugger of a site, and no one wants it. There's no electricity, no development, blah, blah, blah. Let's park our city there. And around it, we've got our industrial constellation as it develops over time. We've got our thorium system. We're going to pull seawater from the sea. Okay, we're going to desalinate it and then send the steam up into a series of reservoirs up into the foothills above the city. And after we've mineral balanced it, we send it back, and that's actually will run our drinking water for the city and run our agricultural belt. It's also our water source for our industrial systems. About half the steam is now available for water, and that can be used to green the whole area around the city. So the city itself will be embedded in a larger biosystems habitat. And while there's a little town there, we will have energy. We will pulling water from the sea that will have water to green like a little, make a little ecosystem.
How many people live in the city?
10,000. A projected 10,000. So where this struggles is for those 10,000 people, we're going to have to put in a lot of infrastructure. Whereas at the moment, we don't have to do that. But this is the concept. Once it's built, and it's built for the purpose of making stuff, we set up like a mine site in the middle of nowhere. We are here for a reason, and then we build it out, and we build it out, and we build it out. So we've got a lot of infrastructure for a comparatively small number of people, but those people have a purpose. So
we need to warehouse people, so a small number of people is not a design. I mean, the problem of the world is to get all the world's people out of cutting down the forest and whatever and get them in some self-sustained unit.
Agreed, but we need to do this in stages. So the whole purpose of this whole project is to develop certain ideas. So this is a gateway project to something else. And that something else could actually be the next evolution along, which then could be something closer to what you're talking about there. But to try to do it in one step, it's easier just for everyone to drop dead because we just don't know how to do it. We socially don't know how to do it. And so that's the...
okay.
This is a demonstration site, Charlie. It's a gateway project to something else. But what that something else is, we don't even know yet till we get this done.
Well, there's there's a lot of questions in the chat.
All right, should we take some questions then, or shall we go finish?
Oh, well, you I guess you could finish. Yeah, we can do it after.
So the development stages go something like that. Once we kick off, there is a development path. Where we're at the moment is due to complications of my current employer, I've not actually formed an entity to be able to take donations for either Promethean Nexus or Vulcan Catalyst. It's also not clear what country I'm going to be in. So it's not clear for the last 6 months. Do I get a job somewhere else? And wherever that somewhere else is, that should be where I set up the entity. When Vulcan Catalyst gets going, wherever it's actually sited is going to be the country of that entity to actually sort of develop the stuff. So the whole thing's been put on ice until I can sort out my personal problems. Meanwhile, I've been putting all my efforts into getting thorium molten salt off the ground, because the big thing that's stopping this is people that don't believe thorium molten salt's real. And so if we can actually sort of get to the point where we can point to physical systems and there's a procurement path, then this becomes a whole lot easier to sell. Okay, we've seen that. Okay, so the three pillars of this. Promethean Nexus is the plan. Vulcan Catalyst is the foundation that secures the capital, the land, the industrial assets, supplies the electricity and the water, and builds the starting seed of the city. Once we actually get the revenue flowing and the investors are paid back, with that money, we build the rest of the project out. When we get to a certain point, we will have the Chrysopia Institute, which is an innovation hub that has the mandate to look at unorthodox ideas and develop useful solutions. Some of those ideas will be demonstrated in the Vulcan Catalyst Industrial Cluster. There's three wings of discussion. One is all the industrial stuff, which we've talked about. The second one is a new relationship with the planetary environment, both research and development, but also application. And the third one is the development of the new social contract. And so the three separate wings that will run in parallel, all coming out of Chrysopia. Coming to a close, build a gateway with a world worth living to our grandchildren. We face a challenging future. There's a choice. We can roll over and die and complain about the situation, or we can work towards a solution with the idea that such a solution will change every time we look at it. These systems fit together, these ideas fit together, and they evolve. Okay, so these are the websites for those who are interested. Fix bayonets and take that hill. All right, that's it. I'm done.
Cool. Thanks. So you're not married to it being in Peru or Chile?
No. So
okay.
Let me stop sharing. So where did we go? So no. Where am I? Okay. So the original idea was in Peru. Then there's a site in Chile alike. Now there's talk of actually putting it up in Australia.
Oh.
I was discussing the idea of getting a job in America, at which point it's, can you put it in the American system? So there's a site out of Colorado that might be useful. The reality is, if I'm successful in putting one of these sites on the ground, about 2 minutes and 11 seconds after I start, about 50 sites will present themselves, and they'll all want to start in parallel. So there'll be I'll be handing off things to other people, and it will start in multiple places. It all comes down to demonstration of certain technologies that if they work, and once they work, well, humans will do what they do.
Well, but based on what you were showing before, it seems like Sweden is going to have the first MSR, right?
They're going to get there first. They've got powerful people with money who are out the gates and doing it.
So have you considered, Norway, Sweden?
Yep, I have.
Mm-hmm.
I have. It's there are the system at the moment is geared for the desert. The idea of being in the Nordic regions is one thing. The plan was to somehow get the mining industry in Australia in particular, but anywhere in the world. The mining industry has sites that are out, quite remote, and they need power, and they don't know how to do it. And solar panels and wind turbines aren't going to help them, and they're frankly terrified.
Mm-hmm.
And so the idea was to park this project near a mine site and use that mine site as protection to get us going. Sweden, there's no reason why it can't happen here. The problem is Sweden, Finland, Norway are convinced they've already got the system of the future, and they're not interested in new ideas. They'll actually take the time to lecture you about how good they are, without realizing that they've got their pants are down around their ankles like everyone else.
Oh, I see. Okay. Yeah.
There's talk of putting it in Hawaii, but dealing with Hawaii is a rare pain in the ass when it comes to try and do anything.
Mm-hmm.
Trying to get like a drilling permit to drill for water in an area that's abundant in water takes 3 years. So the idea of putting up a radical energy technology, that's laughable. Yeah. But lots of people say, "Oh, set up in Malaysia. I will give you an island, or set up in Africa." And then you said, and like in Mozambique, but you look at the site, it's a tiny little site, and it says, "Oh, we don't care. You're gonna have to change your plan to fit our site." So, yeah.
Well, in terms of the population, like based on my calculations, it makes more sense to aim for like closer to 50,000, just so that you have enough specialization to do everything.
It's a demonstration idea.
Mm-hmm.
So the idea to keep it all balanced biophysically, 10,000 is a good number, but the idea is to have several cities that are close to each other and that then would then share facilities between them.
Mm-hmm.
So you've got a series of small towns, if you will, that are part of a network could work. Yeah.
I have a YouTube questioner asking, "What's the plan for defense of the pilot project?"
Aha. So, needless to say, that has been discussed a lot. The real plans will not be discussed here, but the thinking was sort of like this. When you go through history, for example, you look at like how have things gone wrong in the past, and what's been required to prevent things from going wrong. There's things like freedom of speech, freedom of assembly, freedom of movement, freedom of private property ownership, but also the right to bear arms. All those sorts of things are sort of put together. I'm studying very carefully, for example, the Constitution of the United States in its original form. Trying to actually piece all these things together. I'm going down the rabbit hole on how conventional neoclassical economics has failed us. At the same time, how things kept going horribly wrong when they tried things like socialism and communism. And so I'm boiling this all together. For defense, if we've got an industrial site and you've got your conventional, say, security group, let's say we're in South America where they've got drug dealers with guns that do dodgy stuff. If you've got a security force of, say, 5 people with a sidearm, which is what we do in, say, like a Western city, and call that security, that's not going to work. If we've got a militia within the city where everyone is being regularly trained with military-grade weapons and they've got their own weapons with them, one of the things we looked in the game theory set is when, say, a local drug gang would send in, say, a group of 50 people with military-grade weapons to try and disrupt things. If they're facing an armed force that could turn out of, say, 500 strong, and who are actually trained to be so, then that would be something we could work with. Where the trouble starts is when you start talking about 5th-generation hybrid warfare. That's where this project will be vulnerable. And there'll have to be a hybrid warfare response to that, which it's not sensible for me to actually discuss on an international public.
Fair enough.
Needless to say, the biggest risk is if, let's say, we've got the system set up for 10,000 people, but if 500,000 people turn up and sit in their front lawn and say, "We want access to your medical system, we're not going away till you give it to us," the system will fail. They're the sorts of challenges we're looking at. A lot of the questions don't have answers.
So a related question to what you just said, person asked, in this hypothetical city, what happens when some couples decide to have more children than what a steady state would allow?
So that's these are the questions that are actually. But the idea is to start as a private organization, like a mine site. Everyone's there with a job to do, and so you employ the people who come in. They'll have dependents that come with them. Now, legally, you can't sort of dictate terms to those dependents, but you start out as a private organization and you have more control over what happens. For the 10 years it takes to actually pay off the investors, right, while you're building out the rest of the city, there'll be an intense debate about what social contract we should be administering the city in. And the ownership of the operation will fold into we turned over to be the property of the city council in whatever form it takes. So it'll be administered by the city council, owned by the city council, and that's democratically elected by the people who are in the city, with agreements of what counts of the people who can vote and people who can't vote. Right. When people sort of like, how do we let people into the city? How do we get them to agree to come in? That is a discussion that has to be had, because some hard things need to be said there, and that are not conducive to what we consider a free and equitable society that's got us to the point we're in at the moment. The other problem you've got is when you have people come in and their kids come in, but those kids bring with them the woke agenda that's actually used to destabilize civilian populations at the moment. I have this argument with my daughters all the time. That's actually a fifth generation warfare strategy.
Mm-hmm.
And so that's actually for the people in the city who are not necessarily attached to its running, but who live there, who were convinced to take on an agenda that's socially destabilizing, and the city will destroy itself from within. That's another one of the threats that are very difficult to deal with. There are strategies against that, but again, it's not a smart thing to be discussing on an international YouTube call.
Okay, fair enough. And there's a follow-up question. Literal social contract, like part of passing puberty, involves signing a contract? Or
No.
what you mean?
So what we call a social contract, we've got a social contract, for example, with democracy. We live in a nation state where we all vote, and we vote politicians, and those politicians administer our society. That's a social contract. There's a social contract between us and the banking system. We give them our money as a service, and then they give us access to those services in return. The social contract is broken when those banks turn out to be doing dodgy things. For example, what's happening in the silver market at the moment. The social contract is broken. We've got a social contract with the education system.
What's happening in the what market?
The silver market.
Silver. Okay.
Silver. Hilarity ensues after a pattern that's been building for decades. They're all criminals. What a surprise. So there's a social contract between us and, say, the education system where, well, to get a job, we need an education, like a degree. Okay, fair enough. Okay, how do we get a degree? Oh, you've got to go through stages of evolution, education. These are the agreements in our society that hold us together. Right, that's what I mean by social contract. A legal contract to work, well, we're going to start out with an industrial system like a mine site. We'll start with maybe a workforce of, say, 50 people. The thing will start up. We're going to have a thorium molten salt reactor, a desalination plant, and a pyrolysis plant. We're going to make diesel fuel and electricity. So that'll be an industrial site run by industrial people. And it'll be put together like any other industrial site is at the moment. And so that involves, legal contracts and qualified people and all that. They'll bring their families with them, and we're going to build a little town that people live in. And that's the starting seed, and it will develop from there over time. Will it work? I don't know, but we'll give it a go, and we'll see what happens.
There's also mention of Starbase Texas by Elon Musk, the return to the city-state polis. I don't know if... they're saying this has been tech oligarchs' dream since the 90s.
So, so there's two kinds of people that will help us. One is the badly behaved academic that's protected with peer review, protected by tenure, sorry. And the other is the enlightened James Bond villain. I was one, and now I want to become the other. It really is a case of what do we do and how do you set it up? And in the original contract, what we set up, like, what is this operation? And it's got an agreed tenure track to seed power. It's all about seeding power. We're going to have a multi-million dollar industrial site that's going to hand over ownership to a democratically elected council. Really? Will I turn to the dark side and refuse to do that? If you can have something legal to say, well, this is what happens when we reach a certain stage of development. It's in the Constitution, blah, blah, blah.
Mm-hmm. Fair enough. Okay, any more questions from the panel for Simon?
Yeah. This is really you really break the boundaries of systems thinking in a certain way. And it's very interesting to me. It's not my default position. It's too engineering, too technical for my taste, but I certainly find it very interesting. But let me ask you this. It seems to me that it's all based on lots of energy, like when oil came in or coal came in. It's could be that kind of energy revolution that has all kinds of things you can't count on. But if you're successful in making these modular thorium units that are quote unquote safe, at that point, don't you think that the existing socio-industrial complex will latch on to that cheap source of power and plug it into the existing infrastructure, and then make it more difficult to go to the broader take care of all the problems simultaneously perspective that you have?
So you're probably correct in that. I think the future is going to be uneven and all over the place. If I'm successful, I'll be successful on a small scale at my site. If this technology is successful, yes, there's going to be groups all over the world, like what's being planned in Norway, for example, that's just going to plug into the existing system. We're all going to get rich. And and we'll have like a new class of oligarchs that will start up around that. That's probably their intent. I actually think a lot of the challenges we face at the moment are systemic, and many of the systems we're looking at the moment are facing destruction. Will they survive that destruction? I don't know. I don't know the answer to your question, Charlie, because we actually don't know how nasty things are going to get. If we're able to get through this evolution without too much disruption, then what you're suggesting is a probable outcome for at least some parts of the world. So my challenge would be to demonstrate a way of doing things that actually can resolve at least some of the problems we're facing in a more longer term. And then it's up to other people to do something with it. It's going to take me something like 10, 20 years to do this once I've got the money in the land, at which point I'll be in my mid-70s. So what do? I don't know. What I would say, Charlie, is talking to you personally. I don't know if you heard this when I first signed on, but you've inspired me to do a number of things. First, I got your energy biophysics textbook, which you recommended. Then I got Howard Odum's textbook on ecological systems. I'm going to take the resource balanced economy and evolve it. And I'm going to use the ecological systems theory to do it. I'm going to try and base the whole thing in ecological systems theory. I will probably change and evolve accordingly once I do that. And it's going to take time to do that. If I'm successful, the resource balanced economy is a resource management system that will be based in ecological mathematics and how we handle our resources. I'm hoping to write a document which will be an equivalent of Adam Smith's Wealth of Nations or Karl Marx's Das Kapital as a third alternative. Because economic systems so far, historically, are not able to deal with the problems that we are facing with. You look at each of these systems, they're all for another age. So we need a new way of doing things. So what you're talking about, Charlie, is something I'm trying to do. I just haven't done it yet. And I may not be able to do it because we're talking about quite a serious evolution. And if I can't do it, someone else needs to.
Yeah, no, I agree with that. And thank you for the tip of the hat and so forth. But I want to say I've spent most of my professional career trying to unhorse neoclassical economics. And I had thought the book I produced with Kent Klitgard was the equivalent of the Marx or the Adam Smith that you said. When in fact, we called it Energy and the Wealth of Nations. And that has landed with a resounding thud, not even that in the world of economists or economics. So good luck to you. It's a real tough challenge.
So my thing's going to be a fourth alternative then. You've got the third, I'll do the fourth.
All right. Well, I have said, and I have a writer who wants to. Let me just tell you this. My favorite composer, more or less, is Gustav Mahler, and Mahler was known as being a conductor in his lifetime, but not the producer of symphonies. But now he said, when he was dying in 1910, he said, I would like to conduct my symphonies in 50 years. Well, Leonard Bernstein came around 50 years later and conducted his symphonies and made both of them famous. And so there might be hope for that. And I have a writer who's much younger than I who would like to do that. So I'm going to put you in touch with him.
Right.
And we'll see if anything happens. Good luck. I'm 82. I won't be there.
I'm happy to share the stage. I've got a number of ideas in me that need to go somewhere. I talk to people like Steve Keen and everything, but from a history point of view, the broad brush cycles we're looking at, say around the 1600s, we had the Renaissance and the age of reason. So philosophy, what we call science manifested and merged with philosophy, and the world changed. 200 years later, what we call engineering manifested and merged with money, and the world changed. So here we are now at the end of the Industrial Revolution in that form, but now we've got all sorts of things now are very apparent to us in terms of challenges that the existing system of economics cannot cope with. And so you think things like situation awareness will now manifest and merge with the understanding of what's real and what's not. And and then the world will change again. So we need a new system that at its very intrinsic foundation has all the stuff that's in your book. I've got your book, by the way, and it's brilliant. And so I want to use it. And so is it just I just apply your book to the problems I've got, and then that's as far as I go? Or do I develop a new system? I don't know. One way or another, it's going to get used.
Well, good luck.
Luck.
And I give you credit for really system thinking.
It's my wife's laughing at me right now. Yeah.
All right. Well, we've been going over 2 hours, and I know that Dune also wanted to present on geothermal, but I don't know if we have time today. Dune, do you want to unmute?
Sorry, Dune. Shit, I had no idea. Sorry.
Yeah. Well, here, Dune, can you unmute and say a few words?
Have a crack.
Yeah.
Yeah, I don't think there's enough time really, but basically what Simon's saying is that if you've got very, very cheap energy, can you hear me?
Yeah, we can hear you. Go ahead.
Yeah, if you've got very, very cheap energy, there's all sorts of sort of downstream things that can happen from that. I would like to present something on geothermal, which is a little bit out of the ordinary, and I know Dan is very interested in geothermal as well from the point of view of...
Well, Andrii is also very much interested. Him and I go back and forth on the subject. So
do it.
Yeah.
But Simon, you're picking up my bad habits of bogarting the entire meeting, guys. So you're in good company.
So maybe the next meeting will be geothermal focused then.
Sounds like that would be a good idea. Yeah.
Okay. Good.
Dude, I'm so sorry. I had no idea.
We didn't stop you because it was really good, Simon. That's
yeah,
fine.
exactly.
Yeah.
Exactly. Yeah. All right. So is there any closing remarks or questions?
Simon, our journal, Biophysical Economics and Sustainability, did not have enough manuscript flow and has turned down, but we have taken that and moved it over to a new publishing venue, and I invite you to produce a piece summarizing much simpler this idea for this new endeavor that we're doing. I think you should give your details in more technical, more industry journals, but I will write you about that.
Okay. Yes, let's do that. I'm facing headwinds from the people around me in my employment at the moment. What's happened is in 2023, Finland was granted by the European Union Commission a 2.3 billion euro grant to put up a renewable power grid across Finland, and my work became an embarrassment. And so I think I'm being contained and possibly punished. And so that's actually...
You're in good company.
What is Finland doing? A renewable what?
A renewable power grid across wind and solar across Finland where it snows.
So they don't want to hear about an alternative?
Not yet. And there's the same problem in Hawaii. In Finland, they've been told to put solar panels on all houses regardless of orientation and the fact that it snows most, 6 months of the year.
It's like having wind power in Hawaii. That's really valuable real estate, and you're destroying it with wind turbines. It doesn't work. But yeah.
And it won't take long before it shifts, but yeah. And so the answer is, Charlie, I'd love to work with you in some form. Yes, let's talk about it. I'd love to hear your advice on a few things. Yes, let's talk about it. I'm getting the shits with the how things are at the moment where I am, so I'm looking at a new frontier, and becoming a greenhorn ecologist might be something to look at.
All right, and I also hope that those things with Norway work out for you.
Yeah.
But yeah, so how about for the next meeting in 3 weeks on the 5th of February, Thursday, same time?
Yep.
Can I have 10 minutes then?
Simon, I wanted to tell you before we leave that I saw the presentation you just gave on another forum, and that was forwarded to the guys at the Department of Energy. And I know there's at least 6 scientists at the Department of Energy actually analyzing your proposal, just to let you know that's happening. So,
who are you speaking to?
There's a lot of people at the Department of Energy that I know, Charlie. There's a lot of people at the Department of Energy that actually watch this show.
This show?
Yes.
There are people all over the world going through my stuff.
Yeah.
The International Energy Agency follows my stuff. Lots of people support me in an unofficial capacity, but will not support me officially.
Charlie, you have to remember that a lot of the stuff I give, I came out of the Navy's labs. A lot of stuff I present came out of the Department of Energy's labs. I mean, and the Department of Defense also. So that's why you got that connection between a lot of those government labs in this forum.
Well, I used to work at Brookhaven and at Oak Ridge.
Yep. That's another reason why they watch it.
They're watching you guys.
Make sure you didn't violate your security agreement, brother.
So, Charlie, did you want the 10 minutes now or on the next meeting?
Next meeting.
Next meeting. Okay. All right. We'll book you in there.
Dune's got a lead next time. Sorry, mate.
All right. Okay. We'll get Charlie and Dune up first. Okay. And so, Simon, do you want to close out for us?
Yes. Okay. So thanks for your patience. It's been a long presentation. There are ideas that I'm looking at. I'm looking at multiple ideas. We've got to understand that we are part of this natural world, not separate from it, that we can exploit it. So we've got to follow by the rules of the natural world within our own abilities to do so. That being said, human innovation is a thing. And once we actually get to the point of understanding what is needed, we do have the ability to problem solve. But before we get there, our existing system's got to come apart at the seams first, and that won't happen without a fight. So we've got a period of difficulty to get through. But once we get through that period of difficulty, then we can genuinely problem solve and do some genuinely good actions. What I'm saying is have hope for some of us. Not all of us, some of us.
All right. Thank you. And so, as we found you, we leave you in the infinite love and infinite peace of the infinite creator. Go forth, therefore, rejoicing in that infinite power and infinite love that is within you and all around you, my friends. Okay, I've ended the stream.